So let's start our course with some very important terms that is relevant to risk assessment and you need to be aware of. The first term is hazard. Hazard is anything with potential to cause harm in terms of human injury or ill health, property damage, damage to the environment, or a combination of these. Examples of hazards are electricity, radiation, hazardous substances, noise, where all of these are sources of harm and or loss. It's important to note that a hazard is something that causes a harm. So for example, if a worker receives an electric shock from an item of electrical equipment that has a damaged cord, then electricity is the hazard, not the damaged cord. It is electricity that causes the harm, while the damaged cord is the failure in the preventive measures. If the cord was not damaged, then the hazard would still be present where electricity is still running through the equipment. Another important term is risk. Risk is the likelihood or probability that a hazard will cause harm in combination with the severity of injury, damage, or loss that might occur. Example of a risk is the probability of exposure to and being harmed by electricity, in combination of the consequences, which might be death, injury, damage, or loss. Let's make the difference clear with this simple example. The snake here is a hazard or a risk. The snake is a source of danger, so we can consider it as a hazard, while the probability of being harmed by the snake and the severity of the consequences is a risk. Another important term is incident. Incident is unplanned unwanted event which have caused or could have caused injury, illness, and or damage. An incident could be an accident or a near miss. If the incident resulted in injury, damage, or loss, we call it accident. While if it did not result in injury, damage, or loss, but has the potential to do so, we call it a near miss. In this example, we can clearly identify the difference. The picture on the left side shows that materials fall down, but no injury or harm was caused, so that is a near miss. While the picture on the right side shows that materials fall down and the worker was injured, so that is an accident. So these were some terms that are very important to know. Now let's start talking about risk assessment. Risk assessment is simply a process of identifying hazards, assessing risks that they generate, and then either eliminating or controlling those risks. Risk assessment is a process that we are doing automatically all the time. When, for example, you pass the road, you carry out a risk assessment. When you drive your car, you carry out a risk assessment. But of course, this assessment is normally done very quickly and without conscious thought or effort. A workplace risk assessment is simply an extension of this automatic self-preservation mechanism. What are the benefits of risk assessment? By doing a risk assessment, we are preventing death and injuries to personnel, other types of loss incidents such as equipment damage incidents, financial loss that follow accidents, and breaches of law which might lead to enforcement action and or prosecution by courts. There are some criteria for risk assessment to be suitable and sufficient. It should be completed by a competent team, involving managers, workers, and external experts if needed, and it should state the name and competence of the assessors carried out the risk assessment. It should also cover all aspects of work activity, including routine and non-routine activities, and it should identify all the significant hazards and risks arising out of the work. It should also identify all those persons that could be at risk, including workers and others, such as contractors and visitors. Also, people that are more vulnerable to risk, such as young persons, should be identified. They should also evaluate the effectiveness of current control measures to find out whether they are reducing risks to an acceptable level, and to identify other protective measures that are required to control risk to an acceptable level. The level of risk remains after control measures in place should be low, and the risk assessment should be good enough to fulfill legal requirements. Also, the significant findings of the risk assessment need to be recorded, and risk assessment need to be reviewed when needed, for example, periodically or after any change in circumstances. Risk assessment can be described as a 5-step process. The first step is to identify hazards in the workplace, and then to identify the people who might be harmed and how they will be harmed. Then we have to estimate, evaluate, and control risk. Then we record the significant findings and review the assessment and update if necessary. Before risk can effectively be managed, it's important to identify any hazards in the workplace. Hazard identification is the most important step in the risk assessment, as hazards can only be controlled if they are identified. Remember that risk assessment is a tool for identifying all significant hazards that exist in a workplace, all the things that have the potential to cause harm, and it's not a tool for only identifying those hazards that are poorly controlled and ignoring ones that are adequately controlled. Hazards can be classified as physical, mechanical, chemical, biological, ergonomic, and psychological hazards, and we will talk in brief about each of these categories. We'll start with physical hazards. Physical hazards are environmental factors that can harm an employee without necessarily touching them. Some examples of physical hazards are electricity, noise, vibration, and radiation. One example of physical hazards is electricity. Electricity can cause electric shock when a person touches a live surface. It can also cause electrical burns, which might be internal for the body organs or external for the skin. And it might also cause fires and explosions if an electrical equipment exists in explosive atmosphere or near to a combustible material. Another example of physical hazards is noise. The effects of noise can be classified into physical and psychological effects. Physical effects such as noise-induced hearing loss and reduction in hearing sensitivity, and psychological effects such as stress and lack of concentration. Another example of physical hazards is vibration. Exposure to vibration can cause permanent numbness and tingling, blanching of the fingers, swollen joints, and it can end up to reduction in the sensation of touch. Another example is radiation, which can be classified into ionizing and non-ionizing. Ionizing radiation such as alpha and beta particles, gamma rays, and X-rays. And it can cause sickness, hair loss, cancer, birth defects, and death. While non-ionizing radiation such as laser, ultraviolet, and microwaves can cause burns, redness of skin, and cataract. Another type of hazards is mechanical hazards, which are mainly from contact with dangerous moving parts of machinery. Examples of mechanical hazards are entanglement, where loose items such as clothing are caught on rotating parts of machine. Impact, where the body is struck by a moving part of machine, such as robots. Abrasion, where contact is made with a fast-moving surface, such as grinding machines or conveyors. Ejection, where materials ejected from a machine, such as a grinding machine, penetrates the body. Cutting, where contact is made with a moving sharp-edged part, such as a blade. Crushing, where the body is trapped between two moving parts or one moving part and a fixed object. Another type of hazards is chemical hazards, which are caused by exposure to chemicals. These hazards can cause physical and/or health risks. Hazardous substances can be classified into several categories. Harmful is a substance which, if swallowed, inhaled, or penetrates the skin, it can cause damage to health, such as petrol. Irritant is a non-corrosive substance which can cause skin or lung inflammation after repeated contact, such as cement. Corrosive is a substance that will cause chemical burns to human tissue, and they are usually strong acid or alkali. Toxic, which is a poisonous substance which can cause death, such as arsenic. And carcinogenic, which is a substance that can cause cancer, such as asbestos. Another category is biological hazards, which are caused by exposure to virus, bacteria, fungi, and insects. Another type is ergonomic hazards, which are factors in work environment that can cause harm to the musculoskeletal system. Examples of factors that can cause risk are exerting of excessive force, long duration and high frequency of activity, repetitive movement of hand, arms, or fingers, and unnatural postures of the body. The last type is psychological hazards. Psychological hazards is any hazards that affect the mental well-being or mental health of the worker. Examples are work-related stress, bullying and harassment, lone or remote working, violence in the workplace, and fatigue. We will explore different methods that might be used to identify hazards in a workplace as a part of the risk assessment process. One method is workplace inspection. An inspection is a physical observation of the workplace in order to identify any unsafe acts or unsafe conditions. Through inspections, we can discover different hazards that are present in our workplace and need to be considered in the risk assessment. Another technique is job hazard analysis, or JHA. A JHA is a process which evaluates a task so that hazards associated with this task are identified before employees are exposed to the hazards. In order to conduct a job hazard analysis, we need to select the task to be analyzed, then record the steps of the task, and evaluate the risks associated with each step, and then develop and implement the safe working method in order to eliminate or control those risks, and finally monitor to ensure the effectiveness of the safe working method. Another very important technique is the involvement of workers, because their practical experience and knowledge of the process or activity being considered provides a valuable source of information about methods of work and the nature of the risks, and they may also notice hazards that are not immediately obvious to us. Manufacturers' information for equipment or machinery is a very important information source because it may contain hazards and instructions for safe operation and maintenance. When dealing with chemicals, we have to refer to Material Safety Data Sheet or MSDS because they are very useful in identifying the hazards and safe use of chemicals. A typical MSDS for a substance contains the following information: substance and manufacturer's name, chemical composition, limits of individuals' exposure to the substance, health hazards associated with the substance, first aid measures, firefighting measures if the substance is flammable or combustible, spill mitigation measures, safe handling, transport, and storage, personal protective equipment to be used, toxicity data, disposal consideration, environmental impact, and other information. Another very important source of information are incidents and ill health data. They are very useful in gathering information on the root causes of an incident or situations that may have caused an illness, injury, or damage to property, so it will help in identifying less obvious hazards. But we should not only depend on incident ill health data as a source of information about hazards, because a hazard may be very significant but not yet have caused harm and may therefore go unnoticed. Knowledge of the legal standards that apply to a particular workplace will help in identifying significant hazards. For example, knowledge of the law regarding working at height allow a competent assessor to identify if a task is considered as a working at height. After identifying hazards, it's important to identify the different categories of persons who are exposed to each hazard, because this will affect the choice of control measures of the risk. For example, control measures such as training could be used to protect workers, but it's not applicable for the public. The categories of people at risk might include employees that are working for the organization, contractors doing a job for the organization, visitors, and members of the public that can be affected by organization's activities. In some cases, identifying general groups of people who might be harmed by the hazards is inadequate, and a more specific focus has to be applied to a particular types of persons who are more vulnerable to particular hazards, such as new or young workers, persons with a disability, pregnant women, and lone workers. Having identified hazards and the people at risk, the next step in the risk assessment process is to answer a simple question. Is the level of risk generated by the hazard is acceptable, or does it need to be reduced? So risk need to be estimated and evaluated. So what is risk estimation? It is determining the magnitude of the size of the risk. Risk estimation is determined by two factors: the likelihood or probability of the event and the severity of the consequences if the event takes place. And by this simple equation, we can get the level of risk. Level of risk equals to likelihood multiplied by severity. Risk can be described using words such as very high, high, medium, low, or insignificant. In this case, we call it qualitative risk assessment. The problem with these or similar words is that they mean different things to different people, and so they are not used consistently. An alternative approach that is commonly adopted is the semi-quantitative risk assessment, where we break risk down into its two component parts, likelihood and severity, and then simply assigning a score for each of them in order to calculate a risk rating for a particular hazard using the equation risk rating equals to severity multiplied by likelihood. The use of numbers provides a more consistent way of recording the judgment regarding the level of risk and their priority to be controlled. There is no one right or wrong way to apply this semi-quantitative risk evaluation system, where different organizations use different numbers and descriptions of likelihood and severity depending on their circumstances. It's important to notice that the numbers have no meaning in terms of their relative sizes, so it cannot be assumed, for example, that a risk rating of 9 is 9 times the size of risk rating of 1. We have here an example of a scoring system for severity levels. Note that this is not a standard system. As we mentioned before, each organization is using systems that are suitable for their circumstances. Here we are giving a score of 5 for disabling injury, 4 for medical treatment injury, and 3 for the lost time injury, and 2 for first aid injury, and 1 for very minor injury. Same here for the likelihood, where we are giving scores of 5 for the very likely probability, and 4 for likely, 3 for possible, 2 for unlikely, and 1 for extremely unlikely. The judgment regarding the likelihood of the hazard causing harm is more difficult than deciding on the severity of the consequence of the hazard. There are typical factors affecting the analysis of likelihood, such as if the situations happened several times in the past, this indicates that there is a high probability that it will happen again. And also, with increasing the exposure time and number of people exposed to the hazard, there will be a more chance for the harm to occur. Competence of people involved reduce the chance of human errors and consequently reduce the chances of being harmed. Conditions of equipment is also another factor, as if the equipment is defective, there will be a more chance for it to cause harm. Work environment can also affect likelihood. For example, poor lighting can increase likelihood of tripping hazards while walking in the work site. We can then get the level of risk using risk matrix. In the risk matrix, we have both the severity and likelihood numbers represented, and by multiplying them, we will have all possible levels of risk that we might have. So from risk matrix, we can easily get the level of risk. For example, if the probability of a risk is possible, and it might lead to first aid injury, so from the matrix, we can get that the level of risk is 6. Having estimated the magnitude of the risk, we then have to decide if the level of risk is at acceptable level or additional control measures are necessary. The risk that remains once all control measures have been taken into account can be referred to as residual risk. The residual risk might be acceptable if the risk is insignificant and adequately controlled. It might be also unacceptable if the level of risk cannot be justified regardless of any benefits it might bring. In this case, more control measures are needed to reduce the level of risk. It might also be tolerable if the risk level falls between the acceptable and unacceptable levels. Tolerability doesn't mean that it's acceptable, but means that a person is willing to accept the risk so that they might gain certain benefits, and because further control measures are not possible in terms of time and cost. Once hazards have been identified and the levels of risks have been decided, it's necessary to select control measures in order to control risks to an acceptable level. When trying to identify control measures to control risks, we can use the hierarchy of controls. Hierarchy of controls is a list of options arranged according to their importance, effectiveness, or priority, written so that the most effective control measures are at the top of the hierarchy, while the least effective ones are at the bottom. These elements here make the general hierarchy of controls. As you can see, it starts with elimination of hazards, after that hazard substitution or reduction, and then isolation of people from hazard or hazard from people, and then control exposure, and last is PPE or personal protective equipment. You can see from this hierarchy that elimination is the most effective option, while PPE is the least effective one. The first option to control risk is hazard elimination. Elimination is to remove the hazard or avoid doing the task. And it's the most effective method for dealing with hazard because if a hazard is eliminated, then risk generated by this hazard disappears. For example, by using forklifts, we are completely eliminating the risk of manual handling. You need to take care while eliminating one risk because you could inadvertently introduce other risks. For example, in using forklifts to completely eliminate the risk of manual handling, you will introduce some of the risks associated with using forklifts. Often elimination may not be possible or reasonably practicable or even desirable. Risk reduction, while not as effective as elimination, but it might be a more economically viable solution. Risk reduction is replacing a hazard with another that creates less risk. Example is using a trolley in order to reduce the risk of injury associated with manual handling. We can also isolate the hazard by putting barriers between the worker and the hazard. Examples are enclosure of noisy machine in order to reduce exposure to noise. Here, we are isolating the hazard from the worker. Another example is to isolate the worker from the hazard by doing the work in a well-ventilated control room. And also control exposure to a hazard using engineering and administrative controls. Engineering controls include the use of engineering solutions to prevent exposure to hazard. Example is fixing a local ventilation system in order to remove harmful fumes produced from welding operations. Administrative controls are those that rely on procedures and behaviors, such as provision of a safe system of work, permit to work system, supervision to ensure compliance with rules and procedures, training of employees, reduction of the number of people exposed to a hazard, or reduction of exposure time. last element in the hierarchy of controls is the personal protective equipment, or PPE. PPE are the last line of defense against hazards. Examples of PPE are helmet, hand gloves, safety shoes, eyes protection, and safety harness. Why PPE is the last resort? Because it does not remove the hazard. For example, by using hearing protection, we are not removing the hazard of noise. Also, it only protects one person who is the user, and if it fails, it exposes him to danger. Also, its correct use relies on the user, as well as it may not be worn by the user. It may not protect adequately if it's not fitted correctly, or if the selected PPE is not suitable for the task. It may not be comfortable and may interfere with the user's ability to do the job, and it also may increase overall risk by impairing the senses. For example, hearing protection can interfere with users' ability to hear fire alarms. The choice of control measures should take account of the following factors: whether they are short-term or long-term, their effectiveness, and costs. Controls at the top of the list of control measures will be the most effective in reducing the risk, but usually are more expensive and take much longer time to put in place, so it can be viewed as long-term objectives. While controls that are lower in the list of control measures are usually less effective in reducing risk, but they are cheaper options. They can be put into place quickly and give some measure of risk reduction, but their effect is of short duration. Another factor is proportionality. We have to focus on the significant risks that are more likely to cause a significant level of harm, and not wasting time and resources on insignificant risks with low-level outcomes. Another factor is legal requirements and standards. In some circumstances, legislation specifies the controls needed for a particular hazard. In these situations, any selected control measures will have to meet these standards as a minimum. Also, the selected control measures must be such that the user is competent to use them without them creating a risk. The significant findings of risk assessment process should be recorded in order to provide a statement of the hazards in the workplace, the level of risks that they cause, and the action taken to control those risks. There is no standard format for the risk assessments, so different organizations can use different formats that are most suitable to their circumstances. Typical content should include the activities or areas that are covered by the risk assessment, significant hazards that were identified, the groups of people at risk, evaluation of risks and adequacy of existing control measures, further control measures if needed, the date of the risk assessment, names of the persons carried out risk assessment, and the date when assessment should be reviewed. The last step is to review the risk assessment and update if necessary. Risk assessment can be reviewed periodically or in the case of accidents or near misses, where they imply that there is a deficiency in the risk assessment that needs correction. Changes in the legal requirements, so the risk assessment need to be updated to consider these changes. If an audit recommends that the risk assessment need to be updated, and in case of introduction of new activities, equipment, or personnel, where they can introduce new hazards that need to be considered, and in case of new technologies available or new control measures are available to control a particular risks. Let's work on a practical example. In this case study, we will conduct a risk assessment for electric arc welding in a pipeline containing hydrocarbons. We will use this form. Here we have hazards associated with the task and the effects of these hazards on people or equipment. Then risk analysis or risk estimation with no controls in place. Here we identify severity and likelihood and the level of risk. Then here we identify control measures to control those risks, and after that we again estimate the risk with control measures in place. And finally we evaluate the risk to decide whether it's acceptable, tolerable, or unacceptable. We will use this severity rating guidance, where we give scores for severity levels according to the outcomes in terms of human injury and equipment damage. So here we are giving a rating of 5 for multiple fatalities and extensive damage, and we are giving a rating of 4 for single fatality or permanent disability and for major damage for equipment, and a rating of 3 for major injury or lost time accidents and localized damage for equipment, and a score of 2 for minor or serious injury and minor equipment damage, and a rating of 1 for slight injury or first aid cases and slight equipment damage. And we will use this likelihood rating guidance, where we are giving a score of 5 to certain or imminent probability, and 4 for very likely probability, 3 for likely, 2 for may happen probability, and 1 for unlikely. And we will have this risk matrix, by which we can easily get the level of risk when we have the severity and likelihood numbers. And here we have the risk acceptability or tolerability criteria, through which we can decide whether the risk is acceptable, tolerable, or further control measures are needed. So here, for risk levels of 1 and 2, the risk is trivial, where there is no further control measures are required. And for risk levels from 3 to 6, The risk is adequately controlled or tolerable when control measures identified are implemented. And for levels from 8 to 12, further risk reduction measures should be considered. And for levels from 15 to 25, the risk is unacceptable and the activity must be stopped, and we have to seek specialist advice or support. So we will start our risk assessment process with identifying hazards associated with a task. In the welding operation, we could have the hazards of radiation, and also fumes that are generated which can be inhaled by the welder, and we have also electrical hazards, and we have tripping hazards due to materials or cables obstructing the walkways. After identifying the hazards, we will identify the effects of these hazards on people and equipment. So we will start with radiation, which it may lead to potential fires and explosions due to the presence of hydrocarbons, which can lead to potential fatalities and extensive damage to equipment. It can also cause arc eyes and burns to the skin. The severity in this case is 5, as it may lead to multiple fatalities and extensive damage to the plant, and with no control measures in place, we can say that likelihood is certain, so we will give a score of 5. So from the risk matrix, we can get the level of risk, which will be 25. Then we have to think about control measures that we can implement to reduce the risk. We have to ensure that pipelines is vented, drained, purged with inert gas, in order to ensure that it's completely free from hydrocarbons before start welding. We have also to ensure that all combustible and fire hazards are removed away by a distance not less than 11 meters from the welding point, according to the OSHA standard. We can also install fully enclosed fire retardant enclosure around the welding point to control the spreading of welding products. We have also to provide a fire watcher with fully charged and operable fire extinguisher, and he should stay for a period not less than 13 minutes after finishing the job to ensure that the area is safe. We have also to provide continuous gas monitoring to ensure that there is no flammable gases exist, and for any changes in circumstances, work shall be stopped immediately and welding machine shall be turned off. We have also to provide helmets with dark shade lenses to be used by the welder to protect his eyes from exposure to welding radiation. And to protect him from burns, fire retardant coveralls and flame-resistant gloves and shoes shall be always worn by the welder. And in general, the task shall be carried out by only trained and competent personnel. Then we will re-estimate the risk after controls in place. We can say that severity in this case will be major injury, so the score is 3, and the likelihood after controls in place is may happen, so we will give a score of 2, so the level of risk will be 6. We will then evaluate the risk according to the risk acceptability criteria, and we will find out that the level of risk is tolerable. For exposure to welding fumes, it may lead to asphyxiation and respiratory system problems. So we can say that severity level is 3, and likelihood with no control measures in place is very likely, or 4, so the risk level here is 12. The control measures that we can implement are to ensure the welding enclosure is well ventilated in order to avoid accumulation of fumes. We have also to give adequate breaks and minimize exposure time for the welder, and to provide him with respiratory protection equipment such as face masks with filters. After controls are in place, we will re-estimate the risk. We can say that the severity in this case will be slight, so score is 1, and the likelihood after controls in place is likely, so we'll give a score of 3, so the level of risk will be 3. We will then evaluate the risk, and we will find out that the risk level is also tolerable. For the hazard of electricity, it can lead to potential electrocution, which is leading to minor or major injury or fatality. So severity in this case is 4, as it may lead to single fatality, and we can say that likelihood is certain, so we'll give a score of 5. So the level of risk will be 20. The control measures that we can implement are to inspect welding equipment before using, and to check cables for signs of wear or damage, and any worn or damaged cables to be replaced with new ones. And all cables need to be routed away from any sharp edges to avoid cables cutting, and we have to ensure that cables are kept clear from water, as it increases the severity of electric shock. Also, welding machines need to be earthed to protect the user from electrocution, and the task need to be carried out by only trained and competent personnel. Then we will estimate the risk after controls in place. We can say that the severity in this case will be minor injury, so we will give a score of 2, and the likelihood after control measures in place is may happen, so the score is 2, so the level of risk will be 4. And by evaluation of the risk, we will find out that the risk level is tolerable. For the hazard of work area being obstructed by cables or materials, the severity score in this case will be 3, as it may lead to major injury, and we can say that likelihood is very likely, so we will give a score of 4, so the level of risk will be 12. The control measures that we can implement is to keep access and egress to the workplace clear all the times, and to route cables securely away from walkways, and to provide people of suitable PPE such as helmets, safety shoes, etc. And by re-estimation of the risk after controls in place, we can say that the severity in this case will be minor injury, so score is 2, and the likelihood after controls in place is may happen, so we'll give a score of 2, so the level of risk will be 4. And by evaluation of risk, we can find out that the level of risk here is tolerable. In the next slides, I will talk about some advanced techniques of risk assessment. These techniques may be used in more detailed risk assessments, and they are unnecessary in most cases, but provides a systematic methodology for identification of hazards and, in some cases, calculation of failure probabilities for more complex cases. They are used extensively in, for example, quantified risk assessments. They can be used qualitatively and some quantitatively as well. We will start with hazard and operability studies, or HAZOP. HAZOP is a powerful tool developed for dealing with relatively complex systems, such as oil and gas industries, chemical plants, and nuclear power stations, where a deviation from what is expected in one component of the system may have serious consequences. For example, in oil and gas, the release of hydrocarbons can lead to large fires and explosions, which may lead to multiple fatalities and extensive damage to the plant and equipment. The aim of HAZOP study is to identify deviations from design intention and establish necessary safeguards at the design stage. The major feature of HAZOP study is the use of a team. The team should be experienced and skilled in the disciplines relevant to the operation that is covered by the study. And it should include, for example, the designer, production engineers, maintenance engineers, health and safety advisors, etc. And the team should be led by an experienced and independent facilitator in order to support and guide them and ensure that each discipline can make its contribution. The steps of a typical HAZOP study are to first define the systems that will be covered by the study, which might be the whole plant or part of it. Then select the team that will conduct the study and the facilitators that will lead the team. Then we will collect the plant data needed for the study. For example, piping and instrumentation diagrams or P&IDs, equipment manuals, plant layouts, etc. Then we will divide the system into parts, usually called nodes. In the case of chemical plants, for example, this might be a pipeline between a storage vessel and a reactor. And for each part, we will define the design intention, which means what is meant to occur when the plant is operating normally. For example, what is the normal operating temperatures, flows, pressures, etc. Then we will apply guide words to the statement of intention so that every deviation from the required intention is considered. Examples of guide words are no, which refers to negation of intention, for example, no flow; more, which refers to quantitative increase, such as more pressure; less, which refers to quantitative decrease, such as less temperature; and reverse, which refers to logical opposite of design intention, such as reverse flow. Then we have to identify the causes of each deviation, and for each cause, we have to estimate the risk by considering how likely is a deviation, what are the consequences, and how serious are the consequences. Having assessed the risk, we will determine whether the existing control measures are adequate or more control measures are needed, and the final step is the implementation of the required control measures. So let's work on this case study for HAZOP. In an oil refinery plant, a corrosion inhibitor chemical is pumped from a storage tank into pipelines in order to protect pipelines from corrosion. We will conduct a HAZOP study for this node, and to make it simple, we will only consider the no-flow scenario in this example. As you can see, here is the chemical tank, and the inhibitor is injected to the pipelines by means of pump, and the pump has two manual valves, upstream and downstream. So we will use the guide word no with a flow parameter to consider the deviation of no flow of inhibitor is injected into the pipeline. We then have to think about the causes of having no flow of inhibitor. The causes might be any manual isolation valve is inadvertently closed by operators, or the pump might stop working, or we might have inhibitor line broken, or the inhibitor tank is empty. For each of the causes identified, we need to think about the consequences that we might have. All causes will lead to increased corrosion rates in pipelines where no inhibitor is injected. But for the broken inhibitor line, we may have an additional consequence, which is spillage of inhibitor, which can lead to fire as it's a flammable chemical. And for empty tank, it may also lead to pump damage where the pump is running without flow. Then we have to decide the safeguards to control these consequences. For manual isolation valve closure, we need to provide operators with operating instructions. And for pump failure, we need to install a standby pump that we can use in case of other pumps stop working. And for line break, we need to ensure that line is withstanding the operating conditions without failure. And we need also to install firefighting system in order to be used in case of fire due to spillage. And finally, for empty tank, we need to install low-level alarm to alert operators when the level is low in the tank. And we also need to install low-level trip that will stop the pump in case the level is very low and no action is taken by the operator in order to protect the pump from damage. Another techniques are fault tree analysis and event tree analysis. Be careful not to get confused between these two techniques. They are in fact complementary and are often used together, but focus on opposite sides of undesired event. The figure shows how they fit together. Fault tree analysis is concerned with analyzing faults which might lead to undesired event, while event tree analysis considers the possible consequences once an undesired event has taken place. Both techniques can be applied qualitatively or, if we have the data, quantitatively. Now let's start talking about fault tree analysis. Fault tree analysis is a logical assessment process used to identify and analyze events that have led or may contribute to an incident. Fault tree diagram is drawn from top down, and it's starting with the undesired event, which is usually called top event. Then we have to logically work out and draw immediate faults that contribute to that event, and each of these faults may be caused by other faults and so on. So each branch of the tree is further developed until primary failures or root causes of the top event are identified. There are many symbols that are used in the fault tree analysis, and I will mention some of them. The rectangle refers to the top events or sub-events. The circle refers to the root causes or faults. The AND gate means that the output only exists if all of the inputs exist, while the OR gate means that the output only exists if any of the inputs exist. This example shows a simple fault tree for a fire. For the fire, which is a top event to occur, there need to be a fuel, oxygen, and an ignition source. Notice that we are using an AND gate to connect them because all of the three elements, fuel, oxygen, and ignition source, need to be present at the same time for the fire to happen. And for fuel, in this example, there are two possible sources, which could be paper or flammable liquid. And there are two possible sources of ignition, which could be cigarettes or electrical faults. An OR situation applies in each case because it would only need one of these to be present. In the example, we have a single source of oxygen, which is the atmosphere. So in this example, we can say that paper, flammable liquid, cigarettes, and electrical faults are the root causes for the fire. It's important to notice that to prevent fire from taking place, we would first examine the diagram for AND gates. This is because the fire can be prevented if just one of the three elements, fuel, oxygen, and ignition source, is prevented. Fault trees can also be quantified, but it needs relevant data on the probabilities of each of the sub-events. Unlike identifying the root causes of an event under consideration in the fault tree analysis, event tree analysis is concerned with identifying and evaluating the consequences following the event. Event tree analysis is a forward-thinking process which begins with the initiating and desired event, for example, fire, and shows all possible outcomes resulting from this event. And it's accounting for both success and failures of mitigation measures in place that will stop or mitigate the consequences of potential outcomes. In event tree analysis, we have to first identify the initiating event, for example, fire, that may give rise to unwanted consequences. Then we identify the mitigation measures that are designed to deal with the initiating event, for example, fire detection and alarm systems. Then we construct the event tree and describe the potential resulting accident sequences, accounting for both success and failures of mitigation measures. We can then calculate the probabilities and frequencies for the identified consequences or outcomes if data is available. And finally, we compile and present the results from the analysis. Let us illustrate the process with a simple example where the initiating event is a fire. The event tree diagram shows the initiating event on the left, leading to the first mitigation measure. Is the fire detected? The answer to this question is a simple yes or no. So the tree now branches to represent whether the answer to the question is yes or no. Detection of the fire is, of course, the first step in minimizing the consequence of the fire. So now we need to consider those other factors that are necessary that will either minimize the outcome or make the situation worse. In this example, apart from detecting the fire, we have an alarm system to alert persons in the building and an effective sprinkler system to extinguish the fire. The detection system switches on the alarm and then the sprinkler. Each of these measures is considered as to whether it's working or does not working, each leading to a further branch in the tree. At the end of the branches on the right of the tree, you can see the different possible outcomes following the initiating event, depending on the success or failures of the intervening factors. So for example, if the fire is not detected, the alarm will not sound and the sprinkler will not operate. So if the fire is not detected, there will be the worst outcome, which will be extensive damage and possible fatalities. One solution would be to reduce the probability of failure of the fire detection system. However, this is a very critical measure, since if it fails, then the alarm and sprinkler systems will also fail. We can do that by, for example, including a second detector, which is independent of the first. This would mean that both detectors would have to fail, which is a much less likely event. Okay, now I'm finished the course. I hope that you fully understood and enjoyed this course, and please, if you have any questions, doubts, or concerns, do not hesitate to write to me, and I will get back to you as soon as possible. Thanks for watching, and see you in another courses.